welcome to Spotify. So my name is Neville, and here's my contact. So let's start. So a little bit about me. I'm at Spotify since 2011, like shortly after we just launched in the US. I'm right now a member of, so we do a lot of like Hadoop jobs, machine learning jobs, and we figure out what you like, what you listen to, and what you should be listening to, hopefully. And I mostly do data and backend, so data infrastructure like pipeline and tools, and a little bit backend based scaling terabytes of data, terabytes of recommendation to our users every day. And I started using a bunch of really nice tools for doing data stuff. So among them, we do Storm, that's for real-time processing. We also do Scouting, which is a Scala wrapper for cascading, so you can do like basically have a higher abstraction layer on top of MapReduce. We also started to use Spark, which is an in-memory high-performance computation engine that works really well for some of the iterative machine learning jobs like matrix factorization or gradient descent. And our group at least, do a lot of Scala. It's an interesting language. It's very cool, but it has its pain points. Among the things, well, at Spotify, everyone likes music, so I also like music. I like music, and that's actually me playing a lefty guitar. And if you follow the Spotify blog, I also did the visualization hack a while ago. It's a JavaScript hack for visualization, your audio data. So that's a bit about me. Let's move on. So Spotify, everyone knows about Spotify, hopefully. We are a music company. We stream free music to users. There's also Premium, where you get downloads, offline music, and you also get ads-free experience. Here's Spotify in numbers, basically. We're available in 55 markets right now, and we're growing pretty quickly, and we have a lot of songs, a lot of user data that we collect every day. And we have huge amount of user-generated playlists. Basically, user curates all this music, and then we try to mine them and figure out the relationship between music and between, users. And that's Spotify in numbers. So we also like big data, obviously. This is actually our second generation cluster. This one over here. I think it overheated and somehow crashed. That was a while ago. We went through a few generations already. We were on AWS for a while and had our own cluster. It went from 200 nodes to right now I think it's 700. It's one of the biggest Hadoop clusters in Europe. Well. Let's try this one. Oh, much better. Redundancy. Yeah, that's why you always need backup. All right. Yeah. So we handle a huge amount of data every day, and 5,000 Hadoop jobs running every day. I think the recommendation team contribute to maybe hundreds or 1,000 of them, and our team alone generates maybe 100 terabytes a day of data. So what is Storm? In layman's terms, that's how we describe it to people inside Spotify that just started using Storm. So think of it, if you know Hadoop and MapReduce, it's a real-time processing instead of doing batch. And it's similar to Hadoop, except there's no HDFS. So you kind of have to handle data like input and output yourself. So it can be anything. It could be a real-time stream from Kafka or some message queue, and it could be a database. You can eventually write it out to some database or some output stream, which can be another Kafka cluster. And like MapReduce, you have some kind of tuples aggregation and stuff, but you can have many reducer jobs. Think of all the bots where you can chain them together and you can really compose interesting application out of the reusable small components, whereas each bot just capture some inputs, do some processing computation, and generate some output. And a topology is basically a network of such bots connected together. And there are a few other things that's really nice, like fault tolerance and guaranteed messaging processing and delivery. So basically, you can add messages and you can handle failures in your topology, things like that. So it's a little bit introduction to Storm. And let's move on. So Storm and Spotify. We're actually using a fairly old version of Storm. It's 0.80, and we have a 22 node cluster that's independent from our Hadoop cluster. They are running right next to each other in the same data center. Right now, we have 15 topologies running in production. Most of them doing some kind of tracking, monitoring, or analytics, and some of them are actually supporting product features. And I'm gonna cover some of them later in this talk. So the applications include recommendation, obviously, ads targeting, monitoring, and analytics. So everyone knows about this song. This is actually one of our first Storm application. That was late 2012, and it's a real-time map of the song by Rick Axley. I think he made a lot of money out of Spotify from this song. Yeah, so it's a map of showing people listening to that track in real time. And the next one, I kind of grayed out the numbers. I'm not sure if they are like shareable, but this is a market launch dashboard. This is when we were doing the South American launch, so you can see all these countries on the top row, and then there's all these different platforms, different features. So whenever we launch in a couple of new markets, there's usually a war room with devs, QA, operations. They set together because there's like a complicated chain of steps to initiate a new market, like PR campaign, open up user registration, open up Facebook, open up iTunes and Google App Store downloads and all that stuff. So having real-time numbers for tracking what's going on, how many users are coming in every second, that's really helpful. So that's one of the internal tool that we use. It's based on Storm data, and from Kafka and then to Storm. Other users, we have a few other users. One of them is trending track that's used internally for figuring out what's popular right now, last 5-10 minutes, what's increasingly getting traction, like based on the number of user playbacks and stuff. We also do a lot of email campaigns where we send emails to users and track the click-through and delivery rate and all that kind of stuff. That's also tracked via Storm. And then a bunch of application or user experience tracking, like latency, how many milliseconds it takes to start a track, how many milliseconds it takes to load a view or page, and those kind of stuff. So we do a lot of analytics stuff on Storm. So questions so far? Feel free to interrupt me and ask questions. So in the next section, I'm gonna just dig into one of the Storm topologies that we do here. That's actually powering a social feature. So it's from a user's plate all the way up to recommendation. I'm gonna dig into all these different components in a Storm topology. And here's the thing about Spotify, since we have a fairly big Hadoop cluster, and we've been doing MapReduce and data analytics for a while. Storm is not really, we don't really use Storm as a way of doing small batch. I mean, I've been to a couple of companies here since it seems that it's one of the pretty popular use case for doing small batch data analytics. We do that, but we also do most of them on Hadoop. And for us, Storm is really a good way of building distributed application that's doing soft real-time user experience or features like that. Yeah, and let's look at this feature. The one we're gonna talk about is social listening. So your friend listens to some track and it shows up in your feed. This is the first generation. We all have friends like that, you know, just keep jamming on one track and it's annoying. So that's the first generation. Oh, him again. It's kind of a love-hate relationship. Facebook tried that a while ago. They have the buddy feed that keeps popping. Users hate it. They turn it off. I think they just turned it back on like last week or something. So it's now back there again. So this is built without any data analytics tools. It's just using backend pops up messaging. So It is fairly real time. Things pop up almost like within sub-second latency, but it's really spammy. We don't do anything smart with the recommendation. There's no recommendation. We just try to deliver every message to the user. So it's not super interesting, and the engagement rate is pretty low. And also it's really hard to scale because the messaging part, and we use 0MQ actually, and with 4 data centers and like maybe tens of thousands of messages a second, it's really hard to scale. Second take, this one we actually did it on Hadoop with daily batches. So basically we collect data every day, and at the end of the day we generate some Hadoop jobs, go through what the users have listened to over the last 24 hours or 7 days, generate some kind of aggregation. Oh, this guy's listening a lot to this track. The problem is it takes too long to show up. It takes more than 24 hours. The novelty effect just kind of goes away. And also notice this story. Oops, sorry. There's no timestamp on it because we don't. I mean, it's too late. It's not interesting to show the timestamp. So this is the second take. It is easier to scale though, because you just add more Hadoop machines. But then at the same time, every day there's just thousands of jobs spawning up at the same time after midnight because of the daily analytics, rush, and that kind of breaks down once in a while. So the current take, we actually collect data using Kafka. We collect data from most of the production machines, feed them into Storm. Storm does some kind of computation, and then all the way throw it to a backend. That way we can do incremental updates. Basically, we just compute as data comes in. And notice in this case, we actually have 6 minutes ago. That's pretty recent and interesting. You can talk to the guy. That guy actually sits like a few, maybe 20 feet from me. So that's interesting. We discover these kind of serendipitous moments a lot in Spotify. And it's fairly easy to scale. You have a bunch of bouts and spouts. You basically add more parallelism to each layer as they grow. And each layer is kind of isolated, and there's good. It's very you can easily horizontally scale it. So that's why we like it. And I'm gonna explain this a little bit more. Yes. So is that triggered by the song? Yes. Yes. So the user listening to a track, and then it goes all the way through the entire pipeline. So from the user playing, so this is actually what I'm going to talk about next. So user plays a track. All the users in Spotify actually connects to this thing called an access point. That's like a gateway. We have some encryption, and it's pretty beefy. We have like 200-300 of them machines for handling just user connection and the playback. They do all the heavy lifting, and they also track all sorts of user log, like play a track, play an ad, click on something, some app event, all sorts of log. And behind that, there's all sorts of different backends. We have a SOA, like service-oriented architecture, where we have a lot of smaller systems. Each handles something really simple. And for example, like playlist, social, search, storage. So these are the different kind of systems. And all these servers have Kafka producer installed, so they generate log, and the log goes to Kafka. So let's look at how it actually works. And about logging, so this is how our log look like. It's kind of hacky actually. It's a legacy from a couple of years ago. We have this TSV type of log, but actually we do versioning and log type on them. So for example, if you look at, these are the two type of logs. There's an nsound version 21. There's also client event version 15. And oops. What's going on? All right, thanks. Yeah, so we have these sort of message types and the version. We also have converters in Python and Java, so that you can write your MapReduce job either in JVM mode or in Python MapReduce and pass the log. And we also have a centralized repository for all sorts of message types. And we're actually moving to Avro. So these, we actually include them into a schema Avro type. So next. This is how data gets shipped across the globe. So in the middle, we have a big London data center. That's where all clusters like Hadoop cluster and Storm cluster lives. We also have 3 smaller data centers in Ashburn, Virginia, I think, San Jose, and Stockholm. So service machines, backend service machines on those clusters, they have Kafka producer. They ship data to their local Kafka broker, and then it gets shipped to the big Kafka in London. And then that guy looks at the logs, split them by type and timestamp, and then ship them either to Hadoop, where you end up with directory HDFS like client event 2013, 2014, like April 1st, and hour like 00 and stuff. And then in Storm, where you capture these data using Kafka Spout. So the topology that supports the real-time listening kind of looks like this. At first, you have a Kafka Spout that collects end-sound data from user. Whenever user listens to a track, you have an end-sound message that goes through the spout. Then the first layer is a filter, which look at the end-sound events and filter out the uninteresting ones. The second layer is a metadata decorator. Because in end-sound, if you remember in the previous slide, we track username, timestamp, and the track ID. But sometimes we also want to know artist and the album ID. So that guy decorates by looking up or making a GET request to the metadata service and decorates the data. Then there's a listening trigger bot, which detects interesting patterns. Someone's jamming like Rick Astley in the loop, or someone's listening to an interesting track. And then next, we also value privacy. That's why we have a privacy filter. Basically, if you have a setting turned off, like do not publish, you don't want your friends to see it. Oh, Neville's jamming with Rick Astley. That's embarrassing. So at the end of it, there's a publisher. We use the 0MQ transport protocol to publish events through the network. And it's a service-oriented architecture where any kind of service can subscribe to this event stream. So we have a feed backend that subscribes to it and then serve it to the user in your social feed. So that's the overall architecture. This is actually rolled out to 100% of users. Right now, it's on Discover page. It's kind of mixed with all the other type of recommendations, but we're looking at different ways of making it more interesting and interactive. Like users can actually like and play the track, and maybe it generates a feedback to the original user. Oh, someone liked your story. So any questions so far? Yes? Okay, the question is there a reason for using Kafka for the input but not for the output? We use it for the input because it's already there, and Kafka does reliable message delivery. Not for the output because reliability is not the highest concern in this case. Like if we don't recommend the story, user not gonna complain. So I mean, yes, optionally we can use Kafka in the output case as well, but it's just a matter of choice or design decision. And for us, it's for this particular use case, it's okay to lose some recommendation. Some cases maybe not. Like if you're doing ads targeting, you don't want to lose ad targeting opportunity, right? Because then you lose money. So the first part is end-sound. So it does something pretty simple, like if we actually keep track of a lot of attributes, like if the user skipped the track, how many milliseconds the user played in the track. I mean, anything lower than 30 seconds, it's not really interesting. And then we also have context, like if the user played in a playlist view, in a search bar, that's gonna, I mean, if the user search for the track and play it, that's very interesting. But if it's in radio, maybe not, because it's just a random shuffled track. So these are the reasons and contexts. So we look at these and filter out certain events. And next is the metadata decoration bot. So basically, this bot gets some input fields, and the first thing it does is look up the track ID by doing this method on the tuple, and then it looks up the artist and the album ID, and then appends it to the output tuple. So this is what we call a decorator. And we actually have to pass the input fields into the constructor. If you've done Storm or written Storm bots before, you have to declare the output fields before you initializing. Well, you have to declare this method that declares the output fields. So you kind of have to know what your input fields are beforehand. But the good thing about it is it's really reusable. So whoever can just pick up this bot, put it in their Storm topology, and as long as you have this track ID input, you'll get the additional 2 artist and album ID output. This is actually very similar to how scouting or cascading does things to your tuples. Basically, you have a tuple-based records, and then you can append fields to it. And also, it's if you know functional programming, this is actually a monadic design. It's basically you encapsulate the data in some kind of abstraction. And we have similar bots like geo IP decoration, basically by looking at the IP of Anson, figure out where the user is from, and Postgres Memcache get and set. So similar reusable components that we have. And inside this, it's actually a little bit more complex. We're doing a synchronous request, and we try to batch as many requests as possible. So if you look at this, there are actually 2 threads. The bot thread is the main thread where it handles the tuples. There's also a network thread from the RPC library that we use based on 0MQ. So whenever a tuple comes in, it end up in a batch because we want to delay the request or make requests of 100 tracks a time instead of 1 each time. And then it gets scheduled on the other thread. And once your batch fill up, they're sent over the network to the decorator. Yes. We have our own RPC. The question is what kind of API we're using? Not Trident. This is a basic rich bot. Yeah. We haven't found a good use. I mean, this topology is pretty simple, so there's no good reason to use a Trident yet. Yeah. And the network layer, the API is based on top Netty. We actually open source that Netty CMTP. So it's a 0MQ protocol on top of Netty. So basically, you can schedule tracks of 100 and send it to a remote service. Once it's done, you get a callback. The callback puts the decorated data like artists and album IDs back into the queue. Then you can both acknowledge the upstream and also emit the decorated data to the downstream. So that's how it works in a synchronous manner. I mean, we use this particular pattern because most of our RPC libraries are asynchronous. For some cases, like Memcache and Cassandra, most of the libraries are synchronous or blocking, so there's no really need to do that. And then once you get track, artist, and album ID and a bunch of other information, they get fed into the listening trigger. This is where the interest part is happening because you can trigger events based on some kind of rule or pattern. Like if the user search for a track and play it, that's interesting. If the user double-click something from someone else's playlist, that's also interesting. And we keep a rolling counter of how many same artist, album, or track in a row, and that's in memory. And then we use that to trigger repeats. Oh, someone has been jamming this track for 5 times in the last 30 minutes. So, and also there's a rate limiting factor in it. So we don't want to generate too many stories from the same user, because otherwise it just becomes boring. So that's the listening trigger. Next, privacy trigger. That's pretty similar to the metadata lookup. It's also synchronous. The only difference here is we just throw some of them away if the user has privacy turned off. We throw it away. And we also cache it so that we stop processing the user for a while. But in this case, we only cache the privacy on case because We want it to be consistent, because in case the user turned it off later, and we still cache the on setting, and then we'll just keep sending users private information. What's the question? No, right now it's pretty simple, just keeping a particular pattern like reasons and the context, and also the repeats. But this is where we can experiment, actually, just by doing some interesting algorithm or ML, but not rule engine. There are only like 4 or 5 fields, so there's no really need for complex rule engine. Yeah. So this is a privacy bot. That's pretty simple. So at the end, we have to publish the message to somebody else. Again, we're doing SOA, so we have a bot running somewhere. It can be any of the 22 machines in the cluster, but we have a service discovery mechanism. So this bot, when it starts, actually registers itself to the service discovery registry, saying, hey, I'm publishing on this machine at this port. So whoever wants my information can just subscribe to it. And the feed service is the backend that serves data to user. So it looks it up from the registry. The registry is based on DNS, SRV. It's pretty simple, old school technology, but it works. So it creates a 0MQ socket to the bot and subscribe to the events. Of course, you can scale this up as well. You can have multiple bots running on many machines. You can duplicate the messages on all bots. Basically, each bot have 100%. So if one of them goes down, you still get some level of redundancy. And you can have multiple subscribers to the same bot because it's a publishing-based mechanism. So it's multicast to a lot of different nodes. We also have tools for testing this. So basically just saying, okay, here's my service. That's what the name of the service. And the tool will just hook it up and dump messages in real time. It's a pretty nice way for troubleshooting Storm application. So, any questions so far? Yes? 0MQ transport protocol. So 0MQ, I think it's originally implemented in C, but we re-implement in Java, so that, and on top of Netty, so that we can use in all the Java services. I mean, there's also JZMQ, which is a Java process talking through JNI to the C implementation, but then it's a little bit harder to troubleshoot, because there are so many interactions going on. Yeah, it's for us, 0MQ is basically a nicer transport, like a easier TCP, basically. We still have to design our own architecture, like topology and all that stuff. Yes? Uh-huh. Oh, which one? This one? Okay. I see. Cool. That's interesting. Thanks. Any other questions?
Could you talk more on the replay mechanism? Did you build anything into it, like how do you catch exceptions, or say you are calling a service and you just listen to the timeout, or did you build anything else into it? Because sometimes you have this situation where you have a failure which is actually an act. Did you ever come across such?
You mean when I interact with external service?
Yeah.
Right now, it's mostly timeout, because, if there's an exception and timeout and also catch exception, when it happens, we throw the event away, which is okay. So, yeah. This use case is not designed for reliability. It's designed for delivery or availability. Yeah. So, yeah. Over there. We actually, the question is how do you test the applications? We actually do it, well, it's a JVM application, so you can test it locally. We do that, but we just swap the spot, the input, from a Kafka spot to a replay, like sample log spot. Basically, we go to a service machine, sample, let's say, 5,000 events, and then just play it back. Well, debugging, you can do it in your IDE or whatever tools you have by running it locally. I mean, if there's some kind of exception happening on the Storm cluster, well, you can either look at the Storm UI. There's usually some exception logging, or in our case, we actually also have Kafka running on all the Storm machines, so the error log actually gets delivered to a centralized place where you can grab or real-time tell, like. It's another Storm application that catches Storm logs, but yeah, it works. Yeah. Yes. We have a lot of Kafka servers. I think we have 6 in each data center just for collecting local data center log, and then we ship it to the big Kafka, which is like 20 machines. There's latency. I'm not a guy working on Kafka right now, but it's more like minute. If it's across Atlantic, like from US to the data center in London, it could be up to a minute, depending on the network condition. Yeah. We were using 0.7. We're upgrading on our way to upgrading to 0.8, but then it breaks some compatibility. So I think the Kafka team is actually in Stockholm, so someone's working on that right now. So, yes?
Are you using just the Storm UI to monitor the cluster, or are you using something that you
right now, just Storm UI. Storm 08, there's not much like monitoring capability. Storm 09 has metrics built in. We haven't tried that yet. But for our monitoring, like for us as a team building product features, we monitor the user-facing metrics. So if the user stops receiving certain recommendation, that's alert for us, but not what's going on with Storm, because that's just the infrastructure piece. So I mean, the real event that should be attended to, the alert or incident that should be attended to, is the user-facing events or metrics. Yes, I mean, we monitor how many tuples we're receiving from a user perspective. Yeah. I'll actually cover that in the next section. All right, so let's move on to lessons learned so far. We learned a bunch of lessons from using Storm. So first, development process. It's still pretty rudimentary right now. We don't really have any well-defined process. Still in the learning phase. Right. So far, it's one Git repository where each team puts their own topology or application in their own folder, subfolder, and then we have a shared sub-project, which is the common reusable bots, like the Kafka spout or the man cache and the decorator bots that we discussed before. And then also, as we discussed, we sample logs for local development, and every topology kind of follow the same structure. So it detects if you're running in a local or on a remote mode. If it's local, just swap out the spout with a local log playback, so it runs smoothly locally. And also we put all the tunable parameters like parallelism and JVM configuration and all those kind of things into the config file. And that's pretty simple. And problem factory. Everyone working with JVM has seen this before. Dependency hell. This is one particular case where we depend on Guava. Storm actually uses a very ancient version like Guava 10. We use Guava 14 for some of our own stuff, and they have conflicts. So you get like method not found or class not found problem in Storm. And we actually, in Storm, you build this Uber jar, like Maven shaded jar that contains everything you need, and then you ship it to the cluster. But then, since Storm, the JVM starts Storm first and loads the Guava 10, actually or precedes the Guava 14 you're using, then you get an exception. So our solution is kind of hacky, but works. We basically relocate the Guava 14 with the Maven shade jar. There's a relocate function. Basically, it just mingles the bytecode and rename anything that's com.google or something to whatever class path or whatever package name you want. Then they don't, basically you have two copies of the Guava in the same JVM, and they don't conflict with each other anymore. That works pretty well for us. We also use the same technique for jobs that we run on Hadoop, like scouting or cascading. Yes, language choices. Spotify actually has a policy to use, company policy to use support Python and Java. Those are the officially supported language. And those are actually fine for doing basic wiring stuff, like talking to any other JVM libraries like Cassandra, Memcache, because most of the popular choices are in Java anyway, like Astaniax for Memcache, and there's Astaniax for Cassandra. There's Spy Memcache for the Memcached, and we have our own RPC library in Java. Actually, the previous Storm topology has two versions, one in Java and one in Clojure. Clojure is maybe like 200 lines of code in one file. Java is maybe, I don't know, like 4 or 5 files each, like hundreds of lines. So Clojure is more fun for doing interesting algorithmic stuff because it's so easy to just, manipulate data structures like maps, lists, and it's a lot less overhead when you actually focus on the problem than how to write code that actually works. And another thing we haven't tried yet is Scala or Hummingbird. Hummingbird is this Twitter library that does batch and real-time in the same library. So Twitter has Scouting, which is a higher level MapReduce code library. And Hummingbird is like that, but it works both on MapReduce and on Storm. So that's something we wanted to try, but we haven't found a use case yet. But then again, our team has pretty good Scala expertise, so I'm pretty sure we should try that some point in the future. That's language choices. And finally, deployment. So right now we have one shared cluster, so everything is Puppetized. So we can just spin up new machines through Puppet pretty easily. The cluster is shared right now because we don't really have that many jobs running, only 15. And it's been fine, and also because we split the logs, so each topology has a lot less data to process. So if you remember before, we do log splitting in Kafka, so each topology can just subscribe to the particular type of message you're interested in. For example, the listening topology only subscribe to end song, like user playing a track. If it's ads targeting, you might only keep track of that plus ads impression. So instead of subscribing to the entire world of every log message coming through Spotify, which is a lot, which is like terabytes a day. And in the future, I think the goal is to have Storm clusters per team. Since it's all Puppetized, it will be easier to spin up new clusters, and maybe we can have it in multiple data centers. And finally, we have a Yarn cluster. Our Hadoop cluster is actually Hortonworks Hadoop 2.0. We have a bunch of other applications on Yarn like Spark, but Storm on Yarn is something we haven't tried yet, mostly because we don't have a use case. And also there are other considerations like firewalling with the production network and data locality and stuff. So those are the things we haven't figured out yet. And then answer the question of monitoring. We actually monitor it from the user perspective. So this is a graph of a production server and the number of listening stories generated per second. So I think here there's a network glitch. So that's why you lost all the data during this a few hours window, and that actually triggers alarms, and that's our way of dealing with production incidents. I think that's it. Thank you. And also, by the way, we're hiring, so check out our jobs page. And if you have more questions, talk to me afterwards. I think we can take a few more questions right now. Yes? Okay, it's another resource, yet another resource. I don't know what the N is for. Negotiator, okay. So basically, Yang is the resource manager for Hadoop 2.0. So in Hadoop 1.0, everything is MapReduce. Basically, MapReduce figures out what nodes you need and what kind of data you want, like from HDFS and all that stuff. In Yarn, Hadoop is actually decoupled from the resource management layer. So MapReduce becomes, MapReduce. So MapReduce becomes an application on Eon, but you can also run other type of distributed application on Eon, like Spark or Storm. Basically, your application will have some master node that runs on one of the Eon nodes, and then it negotiates with the cluster, like I need 500 machines with 8 gigs of memory each, and Eon figures that out and gives you all these resources, and then you start your application, and it can be anything. It can be, again, like MapReduce or Storm, or even like old school MPI and stuff. Yeah. Yes? The question is how many machines on Storm and what's the next? Oh, I think I have a slide before. We have 22 machines. And we have a lot of messages, 20K per second. That's all the topologies combined. So maybe one of them will deal with, let's say, 10,000 tuples per second. They're usually pretty small. I mean, the biggest one is the incoming log message. That could be like a K or 2, because we have a lot of fields. Each log message has like 100 different fields. Not really, because most of the tuples are pretty small. Once it gets to the first layer of filter, it becomes like 2 or 3, just the ones we want. I mean, we always have a first bout in the chain that's a filter that throws anything else away. Yeah. I think it's pretty standard, like server hardware, like 16 or 24 core and 32 gig memory. Yeah, so pretty standard. Yeah. Yes, some of the other topologies. Did I talk? I mentioned some of these. This is one, but it's not really interesting. This is a very interesting one, the market track, basically keeping track of new users coming in each market. That's powered by Storm. So basically, we monitor like real-time user registration and playback and all that stuff. And also we keep track of the users coming in through each different country market. I mean, these are some of the ones, I mean, most of them are used for performance or user experience tracking. So they are not user-facing feature, but we use them internally to track all these sort of metrics.
Are you using Storm in any situation where you need to persist data or have it be reliable?
Yes, the question is, do we have situation where we need to persist data or reliable? Yes, there are many different ways. We actually have Cassandra and Postgres bot, like at the end of your chain, which just writes to a database. And if you think of it, the listening topology, in the end, and it publishes to another service, which stores it in Cassandra. So it's also persisted on disk. Let's go back to that. Yes, so this topology here. So eventually, it goes to the feed service, and the feed service stores it in Cassandra. Yeah. Yes?
How do you know how many balls and Spark, how many parallel tasks?
Yes. We monitor the memory. I actually have, the question is how do you monitor how many bots and spots to use for each layer, right? It's not a like hard specific like science. It's more like a gut feeling and just try and error, I would say. But I actually have access to the cluster, and I know how much resource my processors are running, and also in the Storm UI you have latency for a lot of the tuple processing. For example, some of these, like these bots that performs external metadata lookup. So since they are batched in like batches of 100 requests in the same batch, you can actually track the tuple latency, because a tuple may not be processed until the batch is full. So we just scale it so that we have reasonable trade-off between latency and also the throughput. And in some other cases, like the listening trigger, which keeps in-memory cache of counter and stuff, you can just do like a simple estimation of based on our current user daily active users, that's like 10 million. And then based on any concurrent user at any point, you kind of estimate how much memory you need on each machine to handle all these data. So it's a rough estimation, but it works.
Yeah. What happens to sync if something in memory? If that ball is gone, you don't care, right?
Yeah, in that case, we don't care. If you care, you probably want to use the main cache instead, but then it increases the latency. So it's a trade-off. Yeah. Yes. The question is, what are some of the problems with Storm? I think it's missing, or it's not. It's still like in a like evolving phase, I would say, and it's missing some of the key things that we would like to have, like for example, monitoring or better understanding of what your topology or like tools for tweaking the topology. And also the version we're running is not super stable, like workers goes on and off, down, like up and down pretty often, like it happens once in a while. So it's not exactly stable yet, but it works for our use case for now. Yeah. We haven't, but Spark streaming sounds really promising. And the Storm way of doing things, since we're still doing the basic like bots and topology, just basically chaining them together, it's not as easy to develop like complex machine learning algorithms, I would say. Spark, on the other hand, gives you a really good abstraction of, you have this mini batch. Spark streaming, you can do Spark streaming mode in Spark as well. Basically, you have this abstract data model like a Scala collection, and then you can do all sorts of higher order function on top of it. So that gives you a lot of possibility for doing like ML updates and stuff. So that's something we want to try, either that or with some input in Storm. Like raw Storm, yes, it works very well for the simple stuff. You just want to build a distributed system. So maybe interact with some external service and you want to process tuples. But once you have some complex business logic or algorithm you want to iterate on, it becomes a little bit cumbersome to think in terms of bots, like what each bot's supposed to do. Whereas in Spark, where you have an abstract data type, you just think of, this is my data, how I'm going to transform it into something more useful, how I'm going to loop through it, apply some function and stuff. So I think that's the way we're looking at it. Yeah. Yes. Yeah. Mm-hmm. Well, they don't have to be. The question is, how do you keep the in-memory cache of the listening trigger in sync? They don't have to be in sync, because when the metadata yields a tuple to the listening trigger, actually group by the username. So the same user's events always go to the same bot. So each bot has information about one single user or a group of users, and they don't have to be synced with each other. And it's I think we're using Guava cache. I mean, it's pretty simple in memory, but has some nice functionality like TTL and expiration. So it works pretty well for us. Yeah. Any other questions? Yes, sir. The Storm is the question is there any system level monitoring? Actually, the Storm is a shared environment. We are not the team administering the Storm cluster. We are one of the feature team developing applications on top of Storm. But for most Spotify production machines, we have basic JVM memory monitoring and rules. And if things happen, these trigger alerts to the SRE and operations team. So we have some sort of memory, monitoring, but not enough, I would say. Yeah. I think I can take one more question if there's any. All right. I guess that's it then. Thank you very much.